Hello everyone. So today is the 10th class of this course entitled as Transition Metal Organometallic Chemistry, its principles to applications. So today we are going to discuss some basic problems regarding on the this organometallic chemistry. So the topic of today's discussion will mainly be focusing on this case of trans effect of the CO molecules and also the transition metal carbonyls or the transition metal carbonylates, the nature of their hydrides and their characters and their relative kind of acidities or reactivities in this case. Hello everyone, I am Anubhav Nath. I am currently a PhD student in the Department of Chemistry at IIT Kanpur. And today, this class is going to take around 45 to 50 minutes. And after that, you can go on with your doubts or queries if you have any. So, we shall start one by one. So let's come to the first question. It is regarding the identification of the correct statement among all the given statements. So the statements are: first is the ligands in mutual transposition compete for the metal d electrons. The second option is the trans ligands weaken each other bonds with the central metal atom. Trans effect plays a crucial role in oxidative addition or reductive elimination reactions. Or four, none of these. So correct options are option 1 and 2. So we will go through all the options one by one. So firstly, the ligands in mutual transposition compete for the metal d electrons. This is actually a correct statement because when the ligands will be placing themselves in their mutual transposition, then because of the effect of the trans effect, they will become the trans bond labile more, and the groups will be labile, so it will be more vulnerable towards attack by any kind of incoming nucleophile or electrophile. So then the mutual transposition both will be weakened, and depending on which one has the better trans effect or more trans effect, will be more, the opposite bond will be more labile and it will be knocked off. So the first statement is absolutely correct in this regard. Then the second question: transition ligands weaken each other bonds with central metal atom. The central metal atom acts as an anchor between these two groups, which will be delivering the trans effect to the opposite direction. Thus, the bond weakening will be happening, and depending on the power of the trans effect or the strength of the trans effect that is happening, the bonds will become more labile. But there is a catch: the trans effect does not play any role in oxidative addition or reductive elimination kind of reactions. Because in oxidative addition, the central metal atom gets oxidized and by 2 unit. So if it is in the plus 1 oxidation state, it will go to plus 3. If it was in plus 2 oxidation state, it will go to plus 4. And in case of reductive elimination, the opposite takes place. So if the metal atom is in plus 2 oxidation state, it will be in 0 oxidation state. If it's in plus 3 or plus 4, it will come down to plus 1 or plus 2 after happening the reductive elimination. But in case of this, trans effect does not play any role, because in case of oxidative addition, the central metal atom and their kind of their octet expansion or their oxidation state, those parameters actually are very important in case of this oxidative addition. In case of reductive elimination also, the position of the angular groups actually take part in main direction. In that case, when the groups are cis to one another, and if the groups can form a mutually strong bond with one another, and the metal is already in some high oxidation state, then reductive elimination takes place. In case of oxidative addition, the metal atom should be in its low oxidation state, that is, it should be electronically rich. And also in case of oxidative addition, the when the groups will be oxidatively added, if their bond is polar, then the groups will be transferred to each other. That is, in case of HCl or methyl chloride, the methyl and the chloro groups will be transferred to each other. In case of the groups are non-polar, that is hydrogen, dihydrogen, or ethane, or in case of less polar point, that is CH3I, that is methyl iodide. In case of these molecules, the two attached groups will be cis to one another. So in none of the cases, the trans effect of the other ligands play any role in determining the happening of the oxidative addition or reductive elimination reactions. So the first option and the second option are actually correct, that the ligands in mutual transposition will compete for the metal d electrons, and also trans ligands will weaken each other bonds with respect to the central metal atom. So these two statements are actually correct. Coming to the second question, you see here is the carbonyl substitution reaction in a 17 electron complex proceeds via which of the following pathways? So the pathways given are the ligand rearrangement, isomerization, dissociative mechanism, or the associative mechanism. You see, in this case, many mechanisms are actually given. So we shall go through each kind of mechanism one by one. First one is the ligand rearrangement. You have seen if some ligands are in some carbocationic behavior, or it has an or extended olefinic network, then via resonance it will be going to its more stable tertiary or secondary form, or more stabilized resonating form than its less stabilized form or less bulkier form. So that is called actually ligand rearrangement. You see, one in this case, the hapticity also changes in case of CP ligands or cyclopentadienyl ligands. They actually play a crucial role in this case. So when it can bind, it is binding eta 1 mode, it's a 2 electron donor. When it is binding to the metal atom in eta 3 mode, it is a 5 electron donor. And when it is binding to the metal atom in a eta 5 mode, it is a 6 electron donor. So that is called a ligand rearrangement. So what is this? Actually, ligand actually changes its own direction. Ligand change its own direction or bonding pathways, or in case of their bonding parameters or their hapticity, in order to get itself accommodated in the metal complex environment. Also, isomerization is also one of the major cases you have seen, like cis to trans or trans to cis. Isomerization also takes place when the the environment around the metal center is more bulky. So in that case, the isomerization takes place. From trans it can go to cis. Cis is a more bulkier or strained form. So from cis it can go to trans or vice versa. So like in this case, also isomerization plays a crucial role. But but whether it actually is happening in case of 17 electron complexes substitution reaction, that we will discuss later. In the third and fourth option, this is dissociative mechanism and the associative mechanism. So in case of dissociative mechanism, what happens? One of the ancillary ligands that is actually bound to the metal complex will dissociate itself and create a vacant space for the incoming group. In this case, this is actually carbonyl. So carbonyl or CO in this case will be actually bound to the metal atom. It is actually coming to get attached to the metal atom. So that in this case, the incoming group is the, or Ig is the carbonyl group, and the leaving group or Lg will be the one that is actually currently or presently bound to the central metal atom. In case of associative mechanism, what happens? You see, in that case, association occurs at first. In that case, the metal complex first accepts the incoming group, and then only after becoming the strained transition metal complex. In case of strained transition metal complex, the strained unstable moiety will release one of the leaving groups, and the incoming groups will again be bound to the metal complex. So in that case, associative mechanism takes place. So these are the given four cases, or you can say mode of action by which the carbonyl substitution reaction takes place. So in this case, it is given it's a 17 electron complex. So 17 electron complex, we can remember what is a 17 electron complex. VCO whole 6, the vanadium hexacarbonyl, it's a 17 electron complex. So if you count the electrons of VCO whole 6, you'll see, like in case of vanadium, it's a 4s2 3d3 system. So in that case, it has 5 electrons, and 6 CO molecules, each one will be delivering 2 electrons. So 6 into 2 plus 5 will be counting towards the 17 electron. So the 17 electron complex is nothing but this VCO whole 6. So in case of VCO whole 6, when it is a 17 electron complex, it will be going via associative mechanism. So in this case, you see the dissociative mechanism also can take place in the associative mechanism. Which one is actually is the major one? So 17 electron complex is a vanadium complex VCO whole 6. So it is a 17 electron system. So it is not an 18 electron valence system. So it is electronically unsaturated but coordinatively saturated. So I have already discussed about this kind of saturation modes, that you what is electronical saturation or what is steric or saturation. So it is sterically saturated because all the six, that is the octahedral complex, all the six sides are actually blocked by CO or carbonyl moieties, but it is electronically unsaturated because one electron is less, so it can accommodate. So in that case, it occurs by associative mechanism. So in case of association, so it what happens, one of the incoming carbonyl substitution, one of the incoming groups will be bound to the vanadium. So from VCO whole 6, it will be going to VCO6L, where L is the incoming group. So now it is a 19 valence electron complex, taking in consideration that this incoming group is a 2 electron donor. So VCO6L, that's the moiety. So now it is an unstable moiety because it is both and sterically saturated. So in that case, one of the CO molecules will be substituted by releasing again the one of CO molecules. So it will again be electronically saturated because from 19 electron it will be again going to the 17 electron system, and previously also it was saturated sterically. Now it is also remaining as sterically saturated. So by this mode, this associative mechanism, this carbonyl substitution reaction of VCO whole 6 molecule takes place. So this is given in the parenthesis. I've given this VCO whole 6 actually reacts 10 to the power 10 times. That is quite well, but faster than the corresponding 18 valence electron compare is CrCO whole 6. CrCO whole 6, Cr is a 6 electron system, 4s2 3d4, and 6 COs will be delivering total 12 electrons. So 12 plus 6 is 18. So you can see how this one electron is actually taking as a crucial role in determining the rate of the carbonyl substitution reaction. You see, in case of CrCO whole 6, it is electronically saturated. It cannot accommodate more than that. That's why the reaction is sluggish in case of CrCO whole 6. But in case of VCO whole 6, since it is one electron down from the 18 electron analog CrCO6, it acts 10 to the power 10 times faster than the chromium hexacarbonyl system. So coming to third question, in the carbonyl substitution reaction, the comparison is given between nickel CO whole 4 and CrCO whole 6. So it is between tetracarbonyl nickel and hexacarbonyl chromium. In both the cases, the metal atom is in zero oxygen state because carbonyl is a neutral donor atom or group, you see. And I've already told in the previous slides also, in the previous classes also, that the low oxygen state is 0 or +1. Thus low oxygen state of metal atom is actually stabilized by the strong pi acidic properties of the carbonyl groups. So the four options given are: CrCO6 reacts faster than NiCO whole 4, NiCO whole 4 reacts faster than CrCO whole 6, the bond energy, that is of D CrCO, is higher than that of D NiCO, or the bond energy of D, that is NiCO, is higher than that of D CrCO. So correct options are options 2 and 3. In option 2, nickel CO whole 4 is actually reacting faster than CrCO whole 6, and 3, the bond energy of DCrCO is higher than that of DNiCO. So firstly, I will say that the bond energy of the CrCO molecule in CrCO whole 6 is much higher. It is actually in the range of 150 to 160 kilojoule per mole. But in case of nickel CO, the DNiCO is actually quite low in that case. It is in the range of 95 to 105 or 110 kilojoule per mole. So you see, these two options are actually self-explanatory and complementary also, because if the bond energy of DCrCO is higher than that of DNiCO, so it is evident that this CrCO whole 6 will not react faster than the corresponding nickel analog. That's why the nickel CO whole 4 complex is actually more responded or reacts quite faster than the hexacarbonyl chromium. So in this case, you will see how these cases are actually taking place. In why the bond energy of the corresponding nickel complex is quite higher. So you see the NiCO whole 4, the Ni is a 4s2 3d8 system in the zero state. So 10 electron system, and 4 into 2 are 8. So 10 plus 8 is 18. So 18 electron system it is. Because CRC holes is also in the previous slide I have stated that it is also a 18 electron system, because 6 COs will be delivering 6 into 2 is 12, and chromium is 6, so 12 plus 6 is 18. So both these complexes, chromium CO whole 6 and nickel CO whole 4, are electronically saturated because both are 18 electron valence electron system. But in case you see there are acidity condition metals and their highest number of oxidation, highest number of valency can be extended to 6. So all the 6 positions are actually bound in case of in this CRC whole 6. But in case of nickel C whole 4, 2 positions are still vacant because it's tetrahedral in nature. That's why it is sterically or coordinatively unsaturated in nature, but it is coordinatively saturated in nature. So electronically both are saturated, but yet coordinatively nickel CO whole 4 is unsaturated. So in that case, in case of carbonyl substitution reaction, the 18 electron complex is happening via associative mechanism. So associative mechanism is actually allowing to react faster. So in this case, nickel CO whole 4 can act in associative mechanism quite well than CRC whole 6. But in this case, CRC whole 6, dissociative mechanism has to take place. So in that case, one of the carbonyl should be eliminated first. This should create a vacant space and electronical unsaturation also in the moiety, and then the incoming group Ig will be bound to the central metal atom. In that case, so in case of CRC whole 6, the dissociative mechanism is fire. But in case of nickel C whole 4, the associative mechanism can take place quite smoothly because two centers or two spaces are actually vacant in case of nickel C whole 4. That's why the nickel C whole 4, the bond energy is also quite higher, and nickel C whole 4 also acts quite faster in case of CrCO whole 6. So that is the reason why options 2 and options 3 are the more the major ones in this case, right statements. Let's come to option 4. In case of option 4, the carbonyl substitution reactions at a 18 valence electron complex proceeds via which of the following mechanisms? So all the mechanisms are actually applied like the previous one, the options given: the associative mechanism, the ligand rearrangement, the dissociative mechanism, or the isomerization. So I have already stated that in case of 17 or 16 valence electron complex, the associative mechanism takes place. That in that case, the incoming group first attaches to the metal complex, and then this unstable moiety or the transitional states liberate one of the leaving groups, and then the incoming group will remain bound to the metal atom, and thus it is going via this dissociative mechanism. But in case of 18 electron complex, mainly the associative mechanism actually cannot take place quite smoothly, because in case of 18 electron system, we can, in case of some keeping aside some selected examples, that's like nickel CO whole 4, in case of 18 electron complex, the central metal atom remains coordinatively and also electronically both saturated. So in that case, it should be able to release release one of its bound groups so that it becomes coordinatively and electronically unsaturated. Then one of the leaving groups will be bound to the metal atom, and then it will be again be the parent complex. So thus, in the case of 18 electron complex, the associative mechanism not, dissociative mechanism is the one that takes place. But this is not a hard and fast rule. It does not mean all the 18 electron complexes carbonyl substitution reaction will be proceeding via the dissociative mechanism only. Associative mechanism can also take place in case of such molecules. One of the major examples is NiCO whole 4. In that case, the associative mechanism can take place because it is tetrahedral in nature, it is 18 electron, it has two vacant spaces ready also, so it can accommodate another group in the central metal atom, and thus initiating the cycle. So this one is regarding the new CO, that is the CO stretching frequency order of the given molecules. So in this case, the question is to arrange the complexes Y3MO CO whole 3. This is the general structure or the formula of the given complex in ascending order of carbonyl stretching frequencies where Y is PCl3, PF3, CH3CN. PCl3 is phosphorus trichloride, PF3 is phosphorus trifluoride, CH3CN is acetonitrile, pyridine, ethylene diamine EN, POME whole 3, or PPH3, that is triphenyl phosphine. This is trimethoxyphosphine. This is trichlorophosphine, this is trifluorophosphine. So four kinds of phosphine are there where the groups attached are different. This is chloro, this one has fluoro, this one has methoxy OMe, this one has phenyl, that is the PPH3. And the other ones are CH3CN, pyridine, and ethylene diamine. So we have to actually arrange these molecules in order, ascending order of their carbonyl stretching frequencies. So here you can see I have given this table where you can actually see how the CO stretching frequencies of all these molecules can actually vary among one another. This is entry 1. The Y group is actually variant in all the complexes. Rest MO CO whole 3 part is fixed. So first one is PF3, then there's PCl3, and this order, this table is actually arranged in order of their descending order of their CO stretching frequency. That you can, is quite evident in case of this, in this last column of the table. 2055, next one is 191991, next one is 1888, this one is 1835, then one is 1783, then one is 1758, and then one is 1746. So now we shall go one by one. First one is trifluorophosphine. So in this case, the CO frequency is the highest one, and the last one is pyridine. In case of the CO frequency, is the lowest one. That is 1746. So how we shall actually be able to explain the order? So the more the pi acidic character of the ligand, that is alkyl ligand Y, the less will be the electron density on the central metal atom, that is molybdenum here, MO. Hence less will be the back donation to the carbonyls, resulting in a higher CO stretching frequency. So we can actually explain this system. You see, when the metal atom is the ligand is actually has a higher pi acidic character, then the electron density of the central metal atom, the in the case of the molybdenum, the back donation actually takes place to the CO. So the more in all the cases, the all the ligands are neutral, so the electronics will not be affected. But in case of when the metal atom is also in zero oxidation state, so metal atom will throw the extra electron density since it is in a low oxidation state. So extra electron density will be thrown to the carbonyl group. So if the extra electron density is go thrown to the carbonyl group, then the CO stretching frequency will eventually get dropped because the electron donation will take place on the pi star LUMO of the CO. Thus, the electronical density of the central metal atom on the CO electron density on the LUMO, that is the pi star on the CO, will be increased, and then the CO stretching frequency will eventually get dropped. So if the Y group, that is the alkyl ligand, so if it has a strong pi acidic character, then it will drag the electron density from the molybdenum. So actually what happens in this case, the competition between Y and CO occurs. So among Y and CO, which one will be more pi acidic in nature, so that will drag the electron density from the molybdenum, and then CO atoms, CO ligands will not experience this much electron density as it was happening earlier or in the neutral MoCO3 state. So the if the Y ligand is having a strong pi acidic character, then it will not allow the central metal atom to remain its low oxidation state. It will be dragging the electron or draining out the electron density from the central metal atom. Then the molybdenum, that is the central metal, will not be able to throw the extra electron density to the CO. And then if it is not able to back donate to CO, then the bond order of CO will not also get dropped, and then only the CO stretching frequency will get hyped. The opposite will happen when the ligand will be a more sigma donor and a less pi acceptor ligand. So in case of more sigma donor or less pi acceptor ligands, these Y ligands will also throw the extra electron density to the molybdenum atom. So the electron density on the molybdenum will be more that was in the last case. So if so in that case the molybdenum will also throw the extra electron density, that is it is dragging from the Y, will be putting towards the head of the CO, and then the CO molecule stitching frequency will also get dropped because the bond order will be lowered. So in that case, we have come to the conclusion that this Y, if it is Y, it is strong pi acidic ligand, then the CO stitching frequency will be quite high because it will not allow the metal to throw the electron density to the CO atoms. But if the Y is a strong sigma donor or pi donor or any kind of donor kind of ligand, or it is not even in kind of pi acidic ligand, then a CO molecules will be experiencing a heavy electron density flow from the metal to themselves. So then the electron density of their bond order will be dropped and the CO stitching frequency also will be dropped. So among all the PF3 or the phosphine or this kind of ligands are given, we have to arrange them in case of that increasing pi acidity. So that increasing ascending order will be the same one that is actually wanted here, the carbonyl stretching frequencies. So among all these, you see PF3 molecules is the most strong or the strongest pi acidic ligand because very strong electronegative fluorine, three fluorine atoms are bound to the fluoride, phosphorus. That's how they will be experiencing this kind of thing. But in case of PCl3, the chlorine electronegativity is much lower than that of fluorine because fluorine has a electronegativity 4 in the Pauling scale. Cl has a electronegativity 3.0 in the Pauling scale. You can argue that why in case of PCl3 and POMe whole 3 the case is down because oxygen is more electronegative than chlorine because oxygen's electronegativity in the Pauling scale lies in the range 3.5. What happens in this case, this OC sigma star bond is also happening is actually also taking place here because in this case this PO or OC sigma star bonds are there. These sigma star are also low lying and that can also actually be occurring in the pi electron density or can have some amount of metal interaction with the metal atoms. So in that case, what happens? So we can discuss this one also in lights of this sigma star orbital bonding. In case of this should occur in the two position, but PCl3 should occur in the third position. But that is not happening here. POMe3 is in the third position, that is CO switching frequency is quite low than that of PCl3. So in case of POMe3, you see that is the oxygen OMe can also donate the electron to the phosphorus atom. POMe3 because oxygen is having a strong plus R effect also. Plus R effect or the mesomeric inductive effect, that donating effect. So mesomeric inductive donating effect is also happening. So the phosphorus electron density is also quite high. So that is also the dragging. So the phosphorus electron density is if happening high, then it can throw the extra electron density to the metal atom. Metal will throw the electricity to the COs, and the stretching frequency will get dropped. So the plus R effect or the strong plus R effect or the mesomeric effect of oxygen is actually taking a crucial role here. In case of PPH3, since it is pH, so it is a sp2 carbon system. That's why the electronegativity is quite low in case of CaSp2 in the range 2.9 to 2.8. That's why in case the CO setting frequency is also low. In case of acetonitrile, ethylene diamine and pyridine, you see this is the acetonitrile. Acetonitrile is a very poor sigma donor but is also a very not a very good pi acceptor also because though the nitrogen is in sp, so it is electronegative also, it's quite good electronegative, but there is no resonance stabilization here. So that's how the electron density is happening or the minus I effect of this is not that much. That's why in this case the sigma donation is also crucial here. So that's why in this case the setting frequency is also low. In between ethylene diamine and pyridine is a strong. They are actually comparable in nature because you see the difference in between their Chardonnay saturation frequency is not that much. It is 1758, it is 1746, it is 1898, and this one is 1888. So the stretching frequency difference between these two moieties are quite low. That is 10 to 12 centimeter inverse. Both of these are actually very good sigma donors because ethylene diamine is a chelating ligand, so they can actually bound to the metal atom quite strongly and can increase the electron density on the central metal atom. In case of pyridine also, pyridine's lone pair is also not actually involved in case of binding involved with resonance with the benzene ring that is actually connect with the ring or the heterocyclic ring, but the pyridine atom lone pair is actually quite concentrated and it can also donate the electron to the central metal atom. It's a very good donor. That's why the central metal atom's electron density gets high and it can throw the extra electron density to the residing COs. That's how the CO switching frequencies also will get dropped. This is the order: pyridine less than ethylene diamine, less than acetonitrile, less than triphenyl phosphine, less than trimethoxyphosphine, less than trichlorophosphine, is less than trifluorophosphine. Since the highest electronegativity minus I effect of the pi acidic character is of PF3, and the highest sigma donation ability is between these two, either ethylene diamine or the pyridine. So this is the actual order. Now we shall come to this part where this is the next part where we will discussing several reactions. So how this kind of hydrides will be reacting with the transition metal carbonyls, transition metal carbonyls. So in this case, this is what happens the first reaction. So this is a product of the following reaction, that is FeCO whole 5, when it is reacted with the sodium trimethoxyborohydride. So what is the product? You see, this is actually a hydride donator kind of agent. It is actually a very good hydride donation agent because it is actually an analog of the sodium borohydride NaBH4. Instead of three hydrogen H atoms, three methoxy atoms are actually here, and it is actually a carbonyl group moiety. FeCO whole 5, 5 into 2 is 10, and Fe is a D6 system, 4s2 36. So 8 electron system. So 10 plus 8 is 18. So it is an 18 electron system. So in this case, what happens? What is the product? So since the methoxy groups are actually electronically releasing or electron donating groups, so they will be increasing the electron density on the boron atom. So this boron hydride bonds hydridicity will be much more in this case. So this hydride will be there transferred to the one of the CO molecules. So they are actually COs are bound, and all are actually carbonyl bound. And since it is bound to the metal atom, so the electrophilic character of the COs are much more. And now also this borohydride molecules is quite activated because of the presence of these electron releasing methoxy groups. So this hydride will eventually attack on one of the CO molecules. So it will be producing a formylate kind of metal formylate kind of complex, and the Na plus will be there because it is hydride is coming, so it is electronically negative, and so sodium plus will be there to balance the charge. So by this way, by treating this kind of metal carbonyl molecules, neutral metal carbonyl molecules with these strong hydride donors, we can actually form this metal carbonyl formate kind of molecules. So carbonyl and formate, both kind of groups are here present, and trimethoxyborane will be eliminating itself as a neutral molecule because BOMe 3 is a very stable molecule. BOMe actually one of the most stable one because it is a trivalent species, and boron actually loves to remain in its trivalent state. Here the boron atom is on its tetrahedral or the four coordinate unstable state, and also it is quite reactive because of the presence of these methoxy groups. So BOMe will be releasing itself by releasing the strain, and these kind of metal formulas will be produced. The next question is regarding the showing an example of disproportionation reaction by the transitional metal carbonyl complex. So disproportionation reactions is which kind of reactions where where is an atom that is present in a intermediate oxidation state will be both oxidized and reduced to form two different kind of species in a same reaction. So if a metal atom is in zero oxidation state, or any species is zero oxidation state, though if such a reaction happens where it will be producing both -1 and +1 kind of oxidation species, then it will be a disproportionation or dismutation reaction. So in this case, it is the reaction given, that is Mn2CO10, that is decacarbonyl dimanganese. It's a very well known yellow colored organometallic complex. When it is reacted with pyridine of 12 moles at a very high temperature, that is 120 degrees Celsius, it actually produces two kind of species. First species is the MnPy6 2 plus, and the second species is MnCO5 minus. So in this case, you can see 3Mn2CO whole 10 plus 12Py is the balanced equation will be producing with on combined release. So all the CO molecules will be eliminated and will be producing 2 moles of manganese Py62 plus and 4 MnCO5 minus. So in this case, you can see this is manganese 0. So in this case, it is manganese plus 2 and it is manganese plus 1. So from 0 state, it is actually going to plus 2 state and also plus 1 minus 1 state. So it is also in this reaction, it is actually getting oxidized, and in this reaction, it is actually getting reduced. So here you can see there are 6 moles of manganese. So I have, so you have to keep in remember the keep this in remembered that total number of oxidation and total number of reduction should be the same. It is not kind of that the each molecule is going to a +5 state and one is going to -1 state. No, in that case it ought to be a disproportionate reaction. Disproportionate reaction, the moles of the molecules will be remaining the same. So you see there are Mn2 system and 3 such molecules are there. So total 6 manganese are there. So also we are producing 2 this manganese and 4 this manganese. So you see in this case it is in zero state. So in the zero state it is going to +2 state here. So from 0 to +2 they are having 2 moles of this. So 2 into 2 is +4. So total +4 oxidation increment is here. And also from 6 manganese they are going to 4 this manganese, 4 of these manganese atoms are in this -1 state. So 4 into -1 is -4. So 4. So it is going to +4 also, it is going to -4 also. So you may go to the argument that from manganese 0 it is going to +2 here and -1 here. So where is the equivalence or where is the parameter? Because the increment is +2 and the decrement is in -1. So no, not in the case, you have to form the balance equation first, and then you have to see how many moles of the central atom has been oxidized or how many moles have been reduced. So again, I am actually repeating that again. These 6 moles of manganese are there. So 2 moles of manganese will be going to the +2 state. So total increment is 2 into 2, that is +4. And these 2 moles of and 4 moles of manganese is going to -1 state. So 4 into -1 is -4. So +4 increment and -4 decrement. So that is actually quite balancing each other. So this is a very popular disproportional reaction where this organometallic Mn2CO10 complex in presence of the strong sigma donor ligand pyridine is going to the +2 state and also going to the -1 state by defining this disproportionation reaction. So coming to the next part, that is the what happens when this VCO whole 6 minus is reacted with a Bronsted acid. So VCO whole 6 minus is a negatively charged metal carbonylate. So metal carbonylates are actually very popular in this regard. So we can think of the countercation as sodium or potassium or any alkali metal cation when it is reacted with a Bronsted acid. So VCO by 6 minus when it is reacted with a Bronsted acid or the proton source H plus, so it is actually gets oxidized and H plus gets reduced. So H plus is going to the dihydrogen molecule is released and it is producing a neutral metal carbonylate, that is VCO whole 6. So in a parenthesis I have given the protic compounds may affect the oxidation of metal carbonylates with the regeneration of the neutral metal carbonyls with concomitant release of molecular dihydrogen. So what happens in this case, the VCO whole 6 minus is an 18 electron system because VCO6 is a 17 electron system. So from 17 electron system, it is actually a 18 electron system is formed, but whenever it is treated with a proton source, so it is needs not to be a Bronsted acid because Bronsted acid is a very harsh source of this proton. But in case of other protic solvents also like methanol, or in case you can think of this ethanol or the such kind of protic kind of solvents, so these protic solvents also affect the this decomposition of this VCO whole 6 minus, that is metal carbonylate to the neutral metal carbonyl. So from -1 it is going to 0, so it is getting oxidized, and H plus it is going to H2 at is 0, so it is getting reduced. So this one is the oxidant and this one is the reductant. So such kind of protic compounds may affect the oxidation of the metal carbonylate. So metal carbonylates here it is getting oxidized to the VCO whole 6. That is a 17 electron system. Now, if we come to the next question, it is comparing the nature of the following different metal hydrides, that is HCO CO whole 4, or the second one is the H2FeCO whole 4, or HFeCO whole 4 minus, or HMnCO whole 5. So these kind of 4 systems are there. All are actually transitional metal carbonyl hydrides. All the in cases that are metal hydrides, also metal carbonylate also. So we have to compare the nature of the following metal hydrides. So if we go to the species, this is A has a pKa in the range 1. So it is a have a comparable acidity with sulfuric acid also even. So you see this is a HCO4. So if it is a hydride but it is acting as a proton, you see the acidity is even compared with the one of the strongest inorganic acid, that is the sulfuric acid H2SO4. So you see the nature of this hydride is not kind of hydride but as a proton. So CO whole 4 minus will be, so this molecule will be acting as CO whole 4 minus and H plus, not as H minus and CO whole 4 plus, because the acidity is quite high. The pK is in the range 1, so the acidity can be compared with sulfuric acid, the very strong inorganic acid. In case of option B, H2FeCO whole 4, the acidity is not that much high. It is not that much because of pK, but it is also quite high because the pK is in the range 4.7, which is comparable with an organic acid, that is acetic acid. In case of HFeCO whole 4, you see because it is already negatively charged, so it will be reluctant to actually release one of the protons. That's why the acidity is even lower. So the pK is 14. That is actually comparable acidity with the water or hydrogen monoxide. But in case of HMnCO whole 5 also, the acidity even will be increased, not to that much, but the acidity pK is 7, so the acidity can be compared with that of hydrogen sulfide, that is H2S. So you see in this case HMnCO whole 5 also. So this kind of complex acidity is that this HCOCO whole 4 complex is having a melting point in the range minus 26. So it is quite unstable. The decomposition point is also minus 26. The IR stretching frequency, that is new MH, is in the range 1934, and the delta 1H NMR ppm is in minus 10. So it is actually quite shielded. Then also the pK is in the range 1. So the 1H NMR delta ppm is minus 10, though the pK is quite low. That is have a comparable acidity. In case of H2FeCO whole 4, the melting point is minus 70. So it is also even more unstable than the corresponding cobalt analog. The decomposition point is minus 10, and the delta I 1H NMR shift region is minus 11.1, though the pK is in the range 4.7, that is acetic acid comparable. In case of HFeCO whole 4, in case of the melting point or the decomposition point or IR setting frequencies cannot be considered because it is quite difficult to trap down such unstable intermediates. So the pK is in the range 14 and the acidity is compared with water. But in case of HMnCO whole 5, the melting point is even low, it is minus 25, but the decomposition point is not that, it is stable at room temperature in its liquefied form. The highest stretching frequency of the molecule is 1783, but the 1H NMR is quite upfield, downfield here in the range minus 7.5. Though the pK is even lower, so the acidity is higher than the corresponding iron analog, so it is 7, and the acidity can be compared with H2A, that is the hydrogen sulfide. The term hydride is actually based on the assignment of the normal oxidation state. So the properties of the transition metal hydrides can vary considerably, but it cannot be related with reactivity. Reactivity is something else, but the transition metal hydrides, the proton responsive behavior or the hydride character, it will be acting as a proton source or the hydride source will be quite different. So the transition metal hydrides behavior range from the hydridic behavior to neutral behavior to protic in character. So we cannot say every transition metal hydride will be acting in the same manner. So now we'll come to the last question of this discussion. So last question is regarding showing two different cases which state different characters of a transition metal hydride complex. So, in this I have already stated in the last slide. Like in this, the two different cases will be here. Transition metal hydride can act from a hydridic character or neutral character or a basic character or a protic behavior. So as proton donor, this is the case. So I have already said that this HCOCO4 has an acidity or the pK quite high in the also comparable acidity with sulfuric acid. So the acidity is quite high, the pK is 1. So HCOCO whole 4, when it is allowed to react with water, so whatever, so it can even protonate water also. So it will be producing COCO whole 4 minus and HCO plus. All of this happens because COCO whole 4 minus is a quite stable molecule. Because you see, cobalt is a 4s2 3d7, so 9 electron system. So 9 electron is even having a negative charge, so it is a 10 electron system. And CO are 2 electron donor. So 4 into 2 is 8, 8 plus 10 is 18. So it is an 18 electron system. That's why from HCO whole 4, so it will not be prone to go to the H minus CO whole 4 plus rather than H plus CO whole 4 minus. Because if it is happening is a hydride donor, then it is be H minus CO whole 4 plus. So then it will be a not it will be a 716 electron system that is not that much stable, because 18 valence electron complexes are quite stable in nature. So that's why this compound has a very high acidity. So this H plus will be getting protonated to the water. So it will be forming this hydroxonium anion and this CO whole for metal carbonylic anion. So this is the example where this metal carbonyl molecule is acting as a proton donor, this hydride. But it can also as a hydride donor, because you see in this case it is C5H5 FeCO whole to H. This is an iron center. This is C, nothing but Cp, the cyclopentrienyl iron dicarbonyl hydride. So when it is treated with a bronze state, that is HCl, so what happens? So its nature is completely opposite to that of HCOCO whole 4. So it is acting as a hydride donor. This hydride will be capturing this proton to eliminate or release molecular dihydrogen, and this Cl minus will be bound to the corresponding center. You see this is iron center, this is a plus one, this is minus one, this is minus one charge. So this is a plus two state. So iron 2 is a 6 electron system. This is 2 electron donor. These are both are 2 electron donors. So 2 plus 2 is 4 plus 2 is 6. 6 plus this is 6 electron donor. 6 plus is 12. So 12 plus 6 is 18. So this is 18 electron system. This one is also 18 electron system. So by the help of 18 electron system, we cannot actually explain this kind of system. But in this case, the hydride character is also playing a crucial role, because you see here the iron center is bound to a very strong sigma donor ligand. So this sigma donor ligand is not this iron CP, this minus is not a very good pi acceptor. Rather, is a very strong sigma and pi donor. So this sigma or pi donor ligand will be delivering electrons toward the central metal atom. Thus, the electron density will be shifting towards the is H. So it will be acting as a hydride, not as a proton. So this hydride will be catching this proton from this bronze acid, and this Cl minus will be actually going to this. This you can also term as a transmetallization or kind of ligand metathesis kind of reaction, because you see this hydride is going here, this Cl is coming here, so a kind of transmetallization is happening here. So also in this case, this is also an 18 electron system, and here this iron molecule will be acting as a hydride donor. So in this manner, you can actually differentiate between the several kind of metal carbonyl hydride molecules, how they can react or in which cases they react. Depending on the metal center or the in metal ligand environment, it will be determined how they will be acting as a neutral donor or the hydride donor or as a proton donor. So with it, I'll be finishing this class. Now you can actually go for any doubts. If you have any, you can put on in the chat box. So I'll be happy to answer those.